Algebraic topology is a branch of mathematics that uses tools from abstract algebra to study topological spaces. The basic goal is to find algebraic invariants that classify topological spaces up to homeomorphism, though usually most classify up to homotopy equivalence. Although algebraic topology primarily uses algebra to study topological problems, using topology to solve algebraic problems is sometimes also possible. Algebraic topology, for example, allows for a convenient proof that any subgroup of a free group is again a free group. Main branches of algebraic topology. Below are some of the main areas studied in algebraic topology. Homotopy groups. In mathematics, homotopy groups are used in algebraic topology to classify topological spaces. The first and simplest homotopy group is the fundamental group, which records information about loops in a space. Intuitively, homotopy groups record information about the basic shape, or holes, of a topological space. Homology in algebraic topology and abstract algebra. Homology is a certain general procedure to associate a sequence of abelian groups or modules with a given mathematical object such as a topological space or a group. Cohomology in homology theory and algebraic topology. Cohomology is a general term for a sequence of abelian groups defined from a cochain complex. That is, cohomology is defined as the abstract study of cochains, cocycles, and coboundaries. Cohomology can be viewed as a method of assigning algebraic invariants to a topological space that has a more refined algebraic structure than does homology. Cohomology arises from the algebraic dualization of the construction of homology. In less abstract language, cochains in the fundamental sense should assign quantities to the chains of homology theory. Manifolds. A manifold is a topological space that near each point resembles Euclidean space. More precisely, each point of an n-dimensional manifold has a neighborhood that is homeomorphic to the Euclidean space of dimension n. Lines and circles, but not figure eights, are one-dimensional manifolds. Two-dimensional manifolds are also called surfaces. Examples include the plane, the sphere, and the torus, which can all be realized in 3 dimensions. But also the Klein bottle and real projective plane, which cannot be realized in 3 dimensions, but can be realized in 4 dimensions. Knot theory. Knot theory is the study of mathematical knots. While inspired by knots that appear in daily life in shoelaces and rope, a mathematician's knot differs in that the ends are joined together so that it cannot be undone. In precise mathematical language, a knot is an embedding of a circle in 3-dimensional Euclidean space, R3. 2 mathematical knots are equivalent if one can be transformed into the other via a deformation of R3 upon itself. These transformations correspond to manipulations of a knotted string that do not involve cutting the string or passing the string through itself. Complexes. A simplicial complex is a topological space of a certain kind, constructed by gluing together points, line segments, triangles, and their n-dimensional counterparts. Simplicial complexes should not be confused with the more abstract notion of a simplicial set appearing in modern simplicial homotopy theory. The purely combinatorial counterpart to a simplicial complex is an abstract simplicial complex. A CW complex is a type of topological space introduced by J. H. C. Whitehead to meet the needs of homotopy theory. This class of spaces is broader and has some better categorical properties than simplicial complexes, but still retains a combinatorial nature that allows for computation. Method of algebraic invariants. An older name for the subject was combinatorial topology, implying an emphasis on how a space X was constructed from simpler ones. In the 1920s and 1930s, there was growing emphasis on investigating topological spaces by finding correspondences from them to algebraic groups, which led to the change of name to algebraic topology. The combinatorial topology name is still sometimes used to emphasize an algorithmic approach based on decomposition of spaces. In the algebraic approach, one finds a correspondence between spaces and groups that respects the relation of homeomorphism of spaces. This allows one to recast statements about topological spaces into statements about groups, which have a great deal of manageable structure, often making these statements easier to prove. Two major ways in which this can be done are through fundamental groups, or more generally homotopy theory, and through homology and cohomology groups. The fundamental groups give us basic information about the structure of a topological space, but they are often non-abelian and can be difficult to work with. The fundamental group of a simplicial complex does have a finite presentation. Homology and cohomology groups, on the other hand, are abelian and in many important cases finitely generated. Finitely generated abelian groups are completely classified and are particularly easy to work with, setting in category theory. In general, all constructions of algebraic topology are functorial. The notions of category, functor and natural transformation originated here. Fundamental groups and homology and cohomology groups are not only invariants of the underlying topological space, in the sense that two topological spaces which are homeomorphic have the same associated groups, but their associated morphisms also correspond. A continuous mapping of spaces induces a group homomorphism on the associated groups, and these homomorphisms can be used to show non-existence of mappings. One of the first mathematicians to work with different types of cohomology was Georges de Rham. One can use the differential structure of smooth manifolds via de Rham cohomology, or check or sheaf cohomology to investigate the solvability of differential equations defined on the manifold in question. De Rham showed that all of these approaches were interrelated and that, for a closed-oriented manifold, the Betti numbers derived through simplicial homology were the same Betti numbers as those derived through de Rham cohomology. This was extended in the 1950s, when Ellenberger and Steenrod generalized this approach. They defined homology and cohomology as functors equipped with natural transformations subject to certain axioms, verified that all existing homology theories satisfied these axioms, and then proved that such an axiomatization uniquely characterized the theory. Applications of algebraic topology. Classic applications of algebraic topology include the Brouwer fixed-point theorem. Every continuous map from the unit and disk to itself has a fixed point. The free rank of the nth homology group of a simplicial complex is the nth Betti number, which allows one to calculate the Euler-Poincare characteristic. One can use the differential structure of smooth manifolds via de Rham cohomology, or check or sheaf cohomology to investigate the solvability of differential equations defined on the manifold in question. A manifold is orientable when the top-dimensional integral homology group is the integers, and is non-orientable when it is zero. The n-sphere admits a nowhere-vanishing continuous unit vector field if and only if n is odd. The Borsk-Ulam theorem. Any continuous map from the n-sphere to Euclidean n-space identifies at least one pair of antipodal points. Any subgroup of a free group is free. This result is quite interesting, because the statement is purely algebraic yet the simplest known proof is topological. Namely, any free group G may be realized as the fundamental group of a graph X. The main theorem on covering spaces tells us that every subgroup H of G is the fundamental group of some covering space Y of X, but every such Y is, again, a graph. Therefore, its fundamental group H is free. On the other hand, this type of application is also handled more simply by the use of covering morphisms of groupoids, and that technique has yielded subgroup theorems not yet proved by methods of algebraic topology. Topological combinatorics. Notable algebraic topologists: Frank Adams, Enrico Betti, Armand Borel, Karol Borsk, Lutz Egbert, Jan Brouwer, William Browder, Ronald Brown, Henry Carton, Charles Ehresmann, Samuel Ellenberg, Hans Freudenthal, Peter Freyd, Pierre Gabriel, Alexander Grothendieck, Friedrich Herzebruck, Heinz Hopf, Michael J. Hopkins, Witold Hurewicz, Egbert van Kampen, Daniel Kahn, Hermann Kunath, Solomon Lefschetz, Jean Leray, Saunders MacLean, Mark Mahowald, J. Peter May, Barry Mazur, John Milnor, John Coleman Moore, Jack Morava, Emmy Noether, Sergei Novikov, Grigory Perelman, Lev Pontryagin, Nikolai Popescu, Mikhail Postnikov, Daniel Quillen, Jean-Pierre Serre, Stephen Smale, Edwin Spanier, Norman Steenrod, Dennis Sullivan, René Thom, Eroshi Toda, Leopold Viertorisch, Hassler Whitney, J.H. C. Whitehead, Alan Hatcher. Important theorems in algebraic topology. Borsk-Ulam theorem, Brouwer fixed-point theorem, cellular approximation theorem, Ellenberg-Zilber theorem, Freudenthal suspension theorem, Hurewicz theorem, Kunath theorem, Poincare duality theorem, universal coefficient theorem, Van Kampen's theorem, generalized Van Kampen's theorems, Whitehead's theorem,